Good afternoon, students. We were discussing about the chemical bonding topic. Chemical bonding topic. In the chemical bonding topic, chemical bonding. In this topic, we were discussing about the valence bond theory, VSEPR theory, and how this one covalent bond is acting as an ionic bond. All these things we have studied in the last class. Today we are going to study about covalent bonds. Covalent bonds shows polarity. Covalent bonds shows polarity. That we need to study it. We know that covalent bond is formed by sharing of electron. Covalent bond is formed by sharing of electron. Mutual sharing of electron. Now, if I consider A2 is a molecule where between the A and A, two electrons will be present. So, between the A and A atom, two electrons is present at the mid of the two atoms. After the sharing of the electron, it is present at the mid of the two atoms. When after the formation of the covalent bond, if electronegative element is present, it's like in the periodic table, across the period, atomic size decreases. When the atomic size decreases, electronegativity character or the electron gain enthalpy value increases. So, almost the p block elements, mainly the group 16th element and the group 17th elements, we are considering as an electron gain enthalpy atoms. So, if more electronegative elements are present after the bond formation, that electrons get attracted by the electronegative element. Consider A2 as an example. In this example, I said this shared pair of electron is present between the atoms. There, A atom is similar to another A atom. So, the electronegativity values of these two atoms are similar, so that this shared pair of electron is present at the mid of the two atoms. Now, if A is bonded with the B atom, this shared pair of electron is present at the mid of the A and B. Consider B is the electronegative one, so that it attracts the shared pair of electron towards itself. Complete something it attracts the electrons. Shared pair of electron towards the B atom. So that A atom gets the partial positive charge, B atom gets the partial negative charge. Let me consider one example, H2 and the formation of HCl. In the hydrogen atom, between the hydrogen atom, shared pair of electron is present. In the HCl, shared pair of electron is present at the center. After sharing pair, after some time, that electron get attracted by chlorine atom, because chlorine is an electronegative element. So chlorine gets a partial negative charge, hydrogen gets a partial positive charge. Okay, so there is no partial charge over on the hydrogen atom, even the second hydrogen atom. Here it forms the two ends, polar ends will be forming. One is a positive end, another one is a negative end. H plus, it's not the plus, it is delta plus. Partial positive charge on the hydrogen, partial negative charge on the hydrogen atom. And this polarity of the molecule is measured using the term magnetic moment. Magnetic moment can be calculated using the formula. Magnetic moment is represented as a mu is equal to E into D. E is nothing but E is atom. D is nothing but the distance between the atom, charge on the atom and the distance between the atom, E into B. And it is measured SI unit of polarity of the molecule is the D, magnetic moment. It is nothing but 3.356 into 10 to the power minus 30 coulomb meter. Now let me take few examples. H2O. In the H2O, oxygen is present at the center, two hydrogen atom, it forms a bent-like structure, lone pair of electron on the oxygen atom. We know that oxygen is the electronegative element, so shared pair of electron get attracted by the oxygen atom. So the net dipole moment on the oxygen atom in this direction. So for this molecule, polarity of the molecule or the magnetic moment of the molecule is not equal to 0. Let me take another example, carbon dioxide formation. Carbon is present at the center, double bond O. Both the oxygen atom pulls the electron towards itself with the equal force. So the net dipole moment for the carbon dioxide mu is equal to 0. Now one more molecule, NH3, ammonia. In the ammonia, on the nitrogen atom, lone pair of electron, and the hydrogen will be like this. We know that nitrogen is the electronegative element. It pulls the electron towards itself, and the net dipole moment on the nitrogen atom in the opposite direction, in the upward direction. So the magnetic moment on the nitrogen in the ammonia is not equal to 0. Another example, phosphorus pentachloride. Phosphorus is present at the center, 1, 2 chlorine atom, 3 chlorine atom, 4, 5. We know that chlorine is the electronegative element. So it pulls the electron in all the 5 directions. So the net dipole moment is equal to 0. So mu is equal to 0. If lone pair of electron is present on the atom, it shows the dipole moment. Sometimes it will not show the dipole moment. See, in the hydrogen fluoride, fluorine attracts the electrons towards itself. So nu is not equal to 0. So this is about the covalent bonds, shows the polarity in nature. What is the dipole moment of the molecule? It will be asking for 1 mark, as well as a competitive part. Application part is important. 2-3 questions will be combining. There the polarity, everything will be given, and the magnetic moment. So all those things you need to calculate it. So it is about the polarity of the molecule. Next, next is hydrogen bond. Next side heading is the hydrogen bond. What is the hydrogen bond? Hydrogen refers itself. Hydrogen should be there during the bond formation. Hydrogen bond is nothing but it is the bond formation between the hydrogen with the most electronegative element. Hydrogen with the most electronegative element. We know that in the periodic table, group 17 elements like fluorine, chlorine, bromine, iodine, and group 16th element and group 15th elements like oxygen and nitrogen. See, these elements we are considering as an electronegative element. When these electronegative elements are combining with the hydrogen, it attracts the hydrogen within the molecule it forms the hydrogen bond. But out of this also, fluorine forms the hydrogen bond, oxygen forms the hydrogen bond, as well as nitrogen forming the hydrogen bond. And these will be forming the hydrogen bond, but chlorine, bromine, iodine will not be forming the hydrogen bond. Let me take an example, formation of hydrogen fluoride, HF. HF is a molecule, another HF molecule, one more HF molecule. It is just force of attraction between the electronegative element with the hydrogen atom. Fluorine with the electropositive element, that is with the hydrogen. So this dotted line indicates that hydrogen bond formation. See, this single line is nothing but a covalent bond. See, here two kinds of the bonds are present. One is a covalent bond, another one is a hydrogen bond. Out of these two bonds, covalent bond is a stronger one because there is the sharing of the electron taking place. But in case of the hydrogen bond formation, it is just a force of attraction between the electronegative element of one molecule to the electropositive end, that is with the hydrogen, and it is 1/10th times weaker than the covalent bond. So it is nothing but a hydrogen bond. Let me take another example, HCl, hydrogen chloride. One more question, in case of hydrogen fluoride, hydrogen bond is present, but in case of hydrogen chloride, hydrogen bond will not be present because see, down the group atomic size increases. Fluorine is smaller atomic size, chlorine is a bigger atomic size. When the size of an atom increases, it will not form the hydrogen bond. So HCl hydrogen bond does not exist, but for the HF this one hydrogen bond get exist. Even see, oxygen and chlorine are diagonally related, isn't it? Oxygen is a group 16th first element, chlorine is a group 17th second element, diagonally related elements. But the atomic size of the oxygen is a smaller one, atomic size of the chlorine is bigger one, isn't it? Atomic number of the oxygen is 8, chlorine is 17. So one more shell is added, 1s2, 2s2, 2p6, 3s2, 3p5. For the oxygen, 1s2, 2s2, 2p6, 2p4, sorry. 1s2, 2s2, 2p4. One more shell is introduced for the chlorine atom. So the size of the chlorine atom is bigger, size of the oxygen atom is smaller one. So oxygen forms the hydrogen bond but not the chlorine. Next one is in the hydrogen bond, it is of two kinds. One is intermolecular hydrogen bond. Another one is inter and the intramolecular hydrogen bonding. Intramolecular hydrogen bonding. Intermolecular and the intramolecular hydrogen bonding. Intermolecular hydrogen bonding is nothing but between the two molecules with the most electronegative element and with the hydrogen. That bond is nothing but the intermolecular hydrogen bonding. Let me take an example of water. Let me take an example of water molecule. Within the water molecule, within the water molecule, within the water molecule you can make out the hydrogen bonding, isn't it? See, this one is a one water molecule, another water molecule. Between the water molecule you can make out the dotted line. That dotted line indicates that's a hydrogen bond. So it is nothing but the intermolecular hydrogen bond. Between the molecules a hydrogen bond is formed. Second one is intramolecular hydrogen bond. Within the molecule itself, oxygen or most electronegative element and into the hydrogen. Best example is orthonitrophenol. N double bond O, single bond OH. Orthonitrophenol, where hydrogen and oxygen, between the hydrogen and oxygen, hydrogen bond taking place. So it is nothing but the intramolecular hydrogen bonding. Intramolecular hydrogen bonding is nothing but within the molecule itself, hydrogen and the most electronegative element, hydrogen bonding taking place. So it is of two types. One is intermolecular and the one is the intramolecular hydrogen bonding. Next is anomalous property of water. Because of formation of hydrogen bonding, we need to study anomalous property of the water. First property is it shows very high boiling point. Boiling point of the water is very high. It is about 100 degrees centigrade. It is due to this one hydrogen bond which is present, hydrogen bond present in between the water molecules. See, this one is one water molecule, another water molecule. Between that dotted line you are writing. That dotted line is nothing but the hydrogen bond formation. So due to this hydrogen bond, breaking of this bond requires some energy. So up to 100 degrees centigrade, up to 99 degrees centigrade, while reaching 100 degrees centigrade, all these hydrogen bond get break. Liquid state of water converted into gaseous state of matter. So it is about the hydrogen bonding. So it shows the high boiling point and maximum density of ice is at 4 degrees centigrade. Maximum density of the ice is at 4 degrees centigrade. We know that ice floats on the surface of the water due to the lesser density. Ice temperature is nothing but 0 degrees centigrade. Now if you raise the temperature from 0 degree to 4 degrees centigrade, 0 degree to 4 degrees centigrade, at least few of the hydrogen bond get break, but above 4 degrees centigrade, almost all the hydrogen bond get break in the ice, so that till 4 degree it will be floating on the surface of the water. After that, that solid state of the ice get converted into liquid state of ice. Okay, so the density will be maximum up to 4 degrees centigrade. Then it will be changing due to the physical state changing. Why the physical state get changed? Due to the breaking of hydrogen bond. Why that breaking of the bond taking place? Due to increasing in the temperature. See, up to 0 to 4 degrees centigrade, anyhow hydrogen bond is get balanced. After that, after 4 degree raising the temperature, hydrogen bond, see this hydrogen bond get a break. See, this one is the isostructure, isn't it? There the hydrogen bond which is present in that, it get break after 4 degrees centigrade. So solid state of ice get converted into liquid state of water. So it is about the hydrogen bonding. Next, another kind of bond. coordinate bond. It is another kind of bond. Coordinate bond is nothing but it is a kind of covalent bond only. Here also sharing of electron is taking place. See, in the covalent bond, sharing of electron is taking place between the two atoms, isn't it? But during the coordination bond, again it is the sharing of electron, but that shared electron given from one atom to another atom or from one molecule to another molecule completely. See, A contains the lone pair of electron. It is completely shared between the A and B. So it is represented by, we are representing as A to B. This arrow mark refers to the electron which is present on the A atom completely gives to the B. That bond we are representing as an arrow mark. Actually, it is also sharing of electron, but we have to differentiate between the coordinate bond and the covalent bond. Coordinate bond we are writing as a single line, but while writing the coordinate bond, you have to show it like a arrow mark. Let me take an example. NH3 plus BF3, and this molecule reaction you have studied in the P block elements. Why ammonia is acting as a Lewis base? Why BF3 is acting as a Lewis acid? Because BF3 molecule is the electron deficient center, NH3 is the electron rich center. So during the formation of the bond between the nitrogen and BF3, lone pair of electron given to the BF3. So the bond you have to write because nitrogen is donating the electron to the boron atom. So the arrow mark you have to show it like this. And one more example, formation of ammonium ion. NH3, see, NH3 containing the lone pair of electron plus H plus ion. Okay. H plus is nothing but 1s1. That electron also removed. Hydrogen is nothing but 1s1. That one electron also removed. So it forms a NH4 plus. Now this lone pair of electron completely given to the H plus ion. It forms the bond is like this, or we can write it as NH4 plus. So this is about the coordinate bond. So all the types of the bonds we have studied. Now coming to the last topic in the chemical body is molecular orbital theory. MOT, molecular orbital theory. We have studied about the VSEPR theory, Lewis core cell structure, as well as VBT. Using one more theory was developed by MOT. It was developed by Mulliken in the year of 1935. He gave some other explanation for the formation of the molecule, whether the sigma bond is formed, whether the pi bond is formed, or where exactly the electron is present after the formation of the molecule. So it is a molecular orbital theory. According to the molecular orbital theory, as in the atoms, electrons are arranged in the different orbitals, isn't it? In the atoms, electrons are arranged in the different orbitals. That different orbitals have got different energies, isn't it? Different orbitals with different energies. K shell, L shell, M shell. Within that shell, orbitals are present. Within that orbitals itself, it has got different energies. Now, during the formation of the molecule, atoms combining with the another atom combining with another atom, it forms molecules. It forms the molecules. Within the molecules, molecular orbital is present. Molecular orbitals are present within the molecular orbital. Electrons are arranged with the different energy levels. In the molecular orbital, electrons are distributed in the orbitals with the different energies. Even in the molecular orbitals also, electrons will be distributed in the different orbitals of the molecules. That orbitals also have got a different energy like an atom. And during the combination of atoms, atoms orbitals get combined with each other. Atomic orbitals get combined with each other. That combining atomic orbitals should have similar energy. In the sense, 1s orbital always combining with 1s orbital of another atom. Consider this is 1s orbital of one atom combining with another atom. That atom should contain the 1s electron. Then only combination of 1s taking place. Or 2s combining with the 2s electrons only, or 2p combining with the 2p only. 1s will not be combining with the 2p. This one is not possible. With the similar energy orbitals only can combine, it forms a molecular orbital. And during the formation of molecular orbital or during the formation of the molecules, during the formation of molecular orbitals, it forms two different molecular orbitals. Two different molecular orbitals are formed after the combination of the two atoms. That two molecular orbitals, one is considered as a bonding molecular orbital, another one is anti-bonding molecular orbital. Bonding molecular orbital and anti-bonding molecular orbital. After the combination of the two atoms, it forms two molecular orbital. In that two molecular orbitals have got different energies. One is bonding molecular orbital, another one is anti-bonding molecular orbital. Bonding molecular orbital have got less energy and anti-bonding molecular orbital have got more energy. So that bonding molecular orbital is considered as a stable one, anti-bonding molecular orbital is considered as an unstable one. Why is bonding is a stable one, while anti-bonding is unstable one? Let me explain using the electrons now. Consider, see this distribution of the electron in an orbital. Distribution of the electron in an orbital is explained using wave function. Wave function we are representing as a sun. Wave function we are representing as an psi. Okay. Now psi is a wave function, that is a orbital combination of A2. Consider two atoms combining with each other, it forms a A2. Now consider wave function of A atom is psi A, and wave function of another atom. Wave function of another atom is A. Okay, now while forming the molecular orbital, as I said, how many number of atomic orbitals are combining? The same number of molecular orbitals are formed. If two atomic orbitals are added molecular orbitals will be forming. Okay, so two atomic orbitals are present means two molecular orbitals should be formed. So psi of molecular orbital athava A2 if you write is equal to psi of A plus or minus psi of A. Plus refers to addition of the atomic orbital. Psi A minus psi A refers to the subtraction of the atomic orbitals. During the addition, it forms a new orbital as a bonding molecular orbital. During the subtraction, it forms a anti-bonding molecular orbital. Bonding molecular orbital and anti-bonding molecular orbitals will be forming. And bonding molecular orbital have got less energy and anti-bonding molecular orbital have got more energy. Why this have got less energy? Why this have got more energy? That we need to know. After formation of the molecule, the electrons which will be present between the nucleus. So these electrons have got less energy. Less energy electrons will be present in the bonding molecular orbital and the antibonding electrons will be present in a space of an atom. In the molecule, not in the atom, not in the molecule. Two nucleus will be, attracted by that electron, but not with like these two electrons. So the electrons which will be present in a space of that molecular orbital have got more energy. The electrons which is present between the atoms have got less energy. So bonding molecular orbital and anti-bonding molecular orbital is formed. Is it clear? And one more thing I need to say here. See, 2p orbital containing 2px, 2py and 2pz. During the addition, always 2px will be combining with 2px only. 2py will be combining with the 2py only. Used to write the dumbbell shape x-axis, y-axis and the z-axis. This will be combining with the x-axis only. So 2px, 2px, 2py, 2py, 2pz, 2pz combination will be taking place. 2pz with the 2px will not be taking place. So, and during the combination, symmetry is formed. Okay. So bonding molecular orbital, anti-bonding molecular orbitals are over, and after the formation of the molecular orbital, two kinds of the bonds we are representing. One is a sigma, another one is a pi. Sigma bond formation and the pi bond formation. Sigma bond is mainly for the s orbital, pi bond is for the p orbital. There also 2pz orbital, if it is involved in the bonding, molecular bonding formation, it forms only the sigma bond due to the symmetry in the orbital. Symmetry in the hereditary. Non-symmetry refers to it will be present in the out of the nucleus or space within the molecule. So 2px and 2py forms the pi kind of bond, and 2pz it is the symmetry one, so it forms a sigma bond. I hope all these are clear. So these are the theoretical part. How we have to represent the electrons, distribution of the electrons. Let me explain the next. Now, representation of Representation of molecular orbital. Representation of molecular orbital. Representation of molecular orbital. How can we represent the molecular orbitals? Now let me rub this also. Atomic orbital. This one is for the molecular orbital. Again, up to here. How to represent the electronic configuration or how to fill the electrons in the molecular orbital, we need to study. Atomic orbital, molecular orbital, atomic orbital. So this is also atomic orbital of one atom. I mean another kind of molecular orbital distribution I need to explain now. Atomic orbital. Consider the first one is 1s. Representing the box is very important. It should be in a straight line. 1s of one atom, 1s of another atom. These two combined will form two molecular orbital. One is 1s sigma 1s star antibonding molecular orbital. Antibonding molecular orbital. Sigma 1s bonding molecular orbital, anti-bonding molecular orbital. Always anti-bonding molecular orbital should be present above the atom. I mean above the orbital, atomic orbital, and bonding molecular orbital should be below the atomic orbital. Not below is there, so it indicates that molecular orbital have got the lesser energy than this one. So it is highly stable one. Next, I am writing the 2s. Sigma 2s, sigma star 2s. 1s, 2s, 2p now. 2p x, 2p y, 2p z. 2p z, 2p y, 2px. And this electronic configuration I am writing for the O2 molecule and the F2 molecule. This one I am writing for the O2, C2 and N2 molecule. O2, C2, N2 molecule. Little bit change in the arrangement of the electrons in the molecular orbital. Sigma 2p z pi 2p y pi 2p x. Here pi star 2p y pi star 2p x. Sigma star 2p z. These two orbitals with the different energy levels. This is how to fill the electrons or writing the electronic configuration according to all the rules. Whatever the rules you have studied in the structure of atom, Otto principle, Hund's rule, Police exclusion principle. Using all these rules, we have to write the electronic configuration. Now I am writing for the filling the out the electron in the oxygen C2N2. Same like the previous one. Sigma star 1s, sigma 1s, bonding molecular orbital. Here also bonding molecular orbital, anti-bonding molecular orbital. These three are bonding molecular orbital. These three are anti-bonding molecular orbital. Anti-bonding molecular orbital. Okay. 2 yes sir. Yes sir. Sigma 2s, sigma star 2s. 2p x, 2p y, 2p z. All the orbitals are degenerate orbital. But these degenerate orbital combining with each other, 2pz with the 2pz only, it forms a symmetrical one. 2pz, 2py, 2px. Pi 2px, pi 2py, sigma 2pz, pi star 2px, pi star 2py, sigma star 2pz. This is how to distribute the electron. Bonding molecular orbital, anti-bonding molecular orbital. Now write in the electronic configuration with the increasing order always. Let me start writing. Sigma 1s, sigma star 1s. You need to fill the electrons. So sigma 1s to sigma star 1s to, like that you need to fill it. Sigma 2s, sigma star 2s. Then sigma 2pz, then pi 2py equal to pi 2px, then pi star 2py equal to pi star 2px, then sigma star 2pz. This is how to fill the electrons in this kind of configuration. Next, for this one, sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, then pi 2px equal to pi 2py, then sigma 2pz, then pi star 2px equal to pi star 2py, then sigma star 2pz. So this is how to write the electronic configuration. So this one is a basic thing you need to remember how to fill the electrons. Now I am going to explain one by one. By taking one examples, please remember this electronic configuration mainly for the oxygen and the fluorine. This one is for the O2, C2, N2. I am going to explain for the hydrogen, helium, lithium, carbon and the oxygen. electrons in the hydrogen atom. Now writing the electronic configuration of hydrogen molecule. Atomic number of the hydrogen is 1. Atomic number of the hydrogen is 1. So the box diagram, same thing. Actually, this diagram no need to write, only you need to write the electronic configuration and the bond order. But without writing this molecular orbital theory, it is a bit difficult to write the electronic configuration. So I am going to write. Without writing this also, you can write for the examination, because this will be asking for the 3 marks question. Write the electronic this MOT of hydrogen, helium, lithium, carbon and the oxygen. These are you need to remember. So 1s sigma 1s sigma star 1s, 1 electron each. During the combination it forms a molecular orbital. 2 electrons first you need to collect, because 1 plus 1 2 electrons first is from the bonding molecular orbital. Now you need to calculate the bond order for the hydrogen atom. For all the molecules you need to do the bond order. Bond order is nothing but the number of bonds which is present between the 2 elements in the molecule. That is nothing but the bond order. But bond order can be calculated using the formula half of the difference between the number of electrons present in the bonding molecular orbital minus number of electrons which is present in the anti-bonding molecular orbital. Now if you apply to the hydrogen molecule, half into number of electrons in the bonding molecular orbital BMO is 2 minus it is 0, so it is equal to 1. So hydrogen to hydrogen single bond is present. Hydrogen to hydrogen single bond is present. So hydrogen molecule exists. Bond order of the hydrogen molecule is 1. And if you write the magnetic property, hydrogen, it is diamagnetic because there is no unpaired electron present in the molecular orbital. Next is after the hydrogen you have to write it for the helium atom. Atomic number of the helium is 2. Atomic number of the helium is 2. That is 1s2. 2 electrons in the 1s orbital. Let me write it here only. 2 electrons in the 1s orbital. Let me write it here only. 2 electrons and 2 electrons. So 2 plus 2, total 4 electrons. 2 is here. 2 is in the anti-bonding molecular orbital. Over. Now, if you write the bond order for the helium molecule He2, half into 2 minus 2 equal to 0, isn't it? 2 bonding molecular electrons and the 2 anti-bonding molecular orbital. So it is equal to 0. So in between helium to helium, this bond does not exist. So helium molecule He2 molecule itself not exist. Now if you write an electronic configuration sigma 1s2 sigma star 1s2 is the electronic configuration for the helium. For the hydrogen atom, if you write the electronic configuration, it is 1s2. And magnetic character, again it is a diamagnetic because there is no unpaired electron in the molecular orbital. So this is about the hydrogen and the helium. Next we are going to write it for the lithium molecule. Lithium molecule Li2, atomic number of the lithium is 3, so the electronic configuration is 1s2 2s1, 1s2 2s1. One is containing the 2 electron, one is containing 2 electron. So total 2 plus 2, 2 plus 2, 4 electron, 2 electron in the bonding molecular orbital, 2 electrons in the anti-bonding molecular orbital. It contains 1 each. 2 electrons in the bonding molecular orbital. Sigma 2s, sigma star 1s, sigma 1s. This one is sigma star 2s. If you write the electronic configuration of Li2, it is 1s2 sigma star 1s2 sigma 2s2 sigma star 2s0. There is no electron over here. If you calculate the bond order, half into number of electrons in the bonding molecular orbital is 4, minus 2 equal to 1. So within the lithium molecule, Li single bond is present. Li single bond Li. It is about the lithium. Next, carbon. C2 molecule, carbon molecule. Atomic number of the carbon is 6. Electronic configuration becomes 1s2, 2s2, 2p2. 1s2, 2s2, 2p2. And for this one, magnetic moment I didn't explain. So it is nothing but it is a diamagnetic one because there is no unpaired electron. All the electrons which is present in the molecular orbital is paired one. So it is acting as a diamagnetic one. Now I am going to continue with the carbon with the same diagram. Now, 1s electron orbital containing the 2 electrons and 2s containing 2 electrons, 2p containing the 2 electron. This one is the atomic orbital of carbon atom, atomic orbital of carbon atom, molecular orbital of C2 molecule. Distribution of these things over. Here 2 plus 2, 4 electrons. Now 2 plus 2, 4 electrons we need to distribute it. 1, 2, 3, 4 electrons. 4 electrons, isn't it? Now calculating the bond order. Calculating the bond order. By calculating the bond order, half into 2 plus 2 4 plus 2 6 7 8 8 minus 2 plus 2 4 8 minus 4 equal to. So between the carbon to carbon bond, double bond is present. C2C double bond is present. I mean only in the C2 molecule we are saying carbon to carbon double bond is present, and it is acting as a paramagnetic one because it contains the unpaired electron in it. So it is acting as a paramagnetic one. And the electronic configuration are sigma 1s, sigma star 1s2, sigma 2s2, sigma star 2s2, then sigma 2p z2 pi 2px1 is equal to pi 2py1. So this is about the C2 molecule. Next, last one, oxygen molecule O2. This one only you need to change it, isn't it? Atomic number of the oxygen is how much? Atomic number of the oxygen is 8. Atomic number of the oxygen is 8. Electronic configuration becomes 1s2, 2s2, 2p, 6. 1s2, 2s2, 2p, 4. Now distribution of the electron. In the 2p orbital, 4 electrons, 1, 2, 3, 4, 2px, 2py and 2pz, 2px, 2py and 2pz, 4 electrons, total 4 electrons. Pi 2px, pi 2py, pi sigma 2pz, pi star 2px, pi star 2py, sigma star 2pz. Sigma star 2pz. Now we need to distribute it. See, the electron present in the 1s2, 2s2, it is as it is, isn't it? 2 electron in the 1s, 2 electron in the 1s, it forms one bonding molecular orbital, another one is the anti-bonding molecular orbital. Next, 2 plus 2, 4 electrons. Now only the distribution of the electron, this one we need to do it. 8 electrons are present, 4 plus 4, 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8 electrons. So this is how distribute the electrons, like in the increasing order. Now, if you calculate the bond order, half into number of electrons, 2, 4, 6, 8, 10. Isn't it? 10 minus 2, 4, 5. different. One is sigma bond, another one is a pi bond. And this one magnetic character is it is acting as a paramagnetic one. Why it is acting as a paramagnetic one? Because it contains lone pair of electron in their molecular orbital. So it is acting as a paramagnetic one. Now if you write the electronic configuration, 1s2, sigma star 1s2, sigma 2s, sigma star 2s2, then pi 2px, pi 2py, how many electrons? 2 to each, then sigma 2pz2, then pi 2px1 equal to star pi star 2py1. So this is the electronic configuration of oxygen molecule. Actually, this diagram you need to draw it. This is not there for the syllabus. In all the examples, it is not there for the syllabus. But the important thing is writing the electronic configuration, writing the bond order, writing the magnetic character. It carries the 3 marks. But without knowing that molecular orbital structure, you cannot write all those things. That's why I have explained in detail. If you feel like it is easy to remember all those things, we remember it. Otherwise, write the molecular orbital diagram so that you feel easy to write all those things. Without knowing these things, you cannot write the electronic configuration or the bond order. So better write the molecular orbital diagram, then calculate the this one, bond order. So this is the end of the topic. So the chemical bonding chapter got over. Actually in your NCERT syllabus, at the end hydrogen bond is mentioned. The hydrogen bond already explained, and other than that everything I have explained. Resonance hybrid, actually I didn't explain, but resonance hybrid I have explained in the Lewis-Cossel dot structure. That dot structure within itself you can write the resonance hybrid of the molecule. Other than that everything I have explained in this topic. And through your group, we are sending the assignment questions as well as important repeated questions. Please go through the important repeated questions, study well for your final examination. Thank you.